Gentlemen, welcome you back for the event. Now, the title would be The Quantum Leap. The quantum communications and cryptography are poised to revolutionize the satellite industry, offering faster, more secure communication links and enhanced data protection. With advancing technology, quantum technologies are expected to become more widespread in a satellite sector, meeting the rising need for secure and efficient communications. The panel will be chaired by Professor Urbasi Sinha, Head Quantum Information and Computing Labs, Raman Research Institute. Can I welcome you here, sir? Do we have Mr. Professor Urbasi here? Okay, please, thank you. The moderator for the event would be Ms. Reena Dayal, CEO Quantum Ecosystems and Technologies, Councils of India. Please, ma'am. In the panel, the speakers would be Mr. Pankaj Kumar Gupta, Head QEPD ISRO. Very welcome, sir. Dr. Rohini Srivastava, National Technology Officer, Microsoft. Can we have a round of applause for them, please? Dr. Anindita Banerjee, Adjunct Scientist, Corporate R&D, CDAC. And last but not the least, Mr. Dilip Singh, CTO, CUNO Labs. We have Mr. Dilip here. Please, sir. Thank you so much. I'll leave the stage to Ms. Reena. Would you like to continue?
Hi. Actually, we would request Professor Urbasi Sinha, who is the chair of the session, to start the proceedings for the session and give us some context as well. Over to you, Professor Sinha.
Thank you very much. Am I audible?
Volume is a little low.
Am I audible? Because
you are audible, but can you?
Am I audible, visible?
Yes.
Reena, you're nodding?
Yes, you are visible.
In the affirmative?
Yeah.
And audible. Yeah, so thanks a lot and apologies for not being able to make it in person. Some last minute commitments came up. And of course, very nice to see all the panelists here who I know, most of whom I know very well. What I wanted to do over the next few minutes is give a context to why we are discussing quantum technologies in Indian Space Congress. It is, of course, very exciting that now we are at a stage where we actually are discussing this in the annual event, which is discussing so many aspects of space. So what I would like to do is ensure that I have the ability to share my screen. Can you kindly confirm what is going on there in terms of, is there any tech support kind of availability? Because I can only share the screen and I can share the pictures of the panelists at this point. My role has been changed. My gender was changed just now, but now my role has been changed and I can't share screen anymore, which is the opposite of what I would have liked. Please. I am a presenter. I'm a presenter and my screen is still you guys, which doesn't help. I have the presentation open on screen. Interesting. Maybe. What do you see? Do you see yourselves or something quantum? Something quantum. Thank you. Okay, so this is going well so far. So I also see you guys in my bottom portion. So okay, so now with all this sorted out, so this is she/her. I'm Professor Urbasi Sinha. I'm at the Raman Research Institute in Bangalore. And so what I'm going to do over the next 20 minutes or 25 minutes as I was given is set a context for why we are having this discussion. And, to say, why we are also excited about discussing quantum technologies even in the space sector. We are having a lot of discussions on quantum technologies, so people might be under an apprehension now we want to take over the space sector as well. But then that is not true. It is actually something very relevant and we will benefit each other from this particular conversation and the work that we can do. So in that, the topic that I want to discuss more about is quantum communication. Our person who introduced us actually already told us about quantum security, quantum communication, but this is not an area which I suppose most of the people are particularly aware of who are traditionally from the space sector. So I'll spend a few minutes telling you why we need this topic, why we need to discuss quantum in space, and then a few minutes as to why I'm chairing this session, which must mean that we have done something relevant in this topic, right? So why you should worry? Well, you should worry if you are actually responsible for any of these 3 or 4 applications that I have pointed out. So we are all buying things using credit card, online banking. We are also voting a lot these days. Next year is very special for our country. And then, of course, we have the defense strategic communication, which not all of us are doing, but perhaps Pankaj is doing a little bit, given that he is from ISRO. So then these are all examples of, technologies that we are using in our daily lives, which actually involve strategic communication. So you don't want to actually give your credit card details to an unintended party, or online banking details. So some of us may not have a lot of resources in the bank from the academic sector. I represent academia, which is the poorest of the people in the panel discussion. But then still, I don't want it to go away to a random individual if I leave something for my daughter. So it is as serious as that, we need to ensure that the information reaches the right party. And what are we doing now? We are doing this by using what is called classical cryptography. So we have the information, we encrypt it in what is called a key, K-E-Y, string of zeros and ones. We send it over, Anindita receives it if she is the intended recipient, and she has the key. She then decrypts it, and she and I share the information, which is all nice. So we don't want any third party or an eavesdropper to have this information. So what is the problem then with all this? It all sounds very nice. So what is wrong or what is suboptimal is that unconditional security is not possible using the kind of means we are using now. For instance, here we have a smiling scientist, Peter Shor, who came up with what is called the Shor's algorithm, which will actually break the hardness of an important class of problems on which classical cryptography is based. So now I'm saying that 3 times 7 is 21, and I'm asking Rohini, what are the prime factors of 1, 1, 2, 3, 7, 1? I see she's smiling, but she will not be able to give me the prime factors as quickly as 3 times 7. That is because factorization is a hard problem, and we are using that as the basis for our security. But Peter Shor comes up with an algorithm which makes factorization an easier problem on a quantum computer. So then that security itself is completely compromised. And this is what public key cryptography is based on. Computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. We can have new algorithms for classical computers. We can have realization of quantum computers, which is happening very, very rapidly these days. So my security should be independent of future advancements in computational power, new algorithms or new technology. That is, it should be future secure. So this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. So a quantum solution to a quantum problem, and in that the most important part is what is called the distribution of this key, which is what is made secure using laws of quantum mechanics. I don't want to give you a lecture on how quantum mechanics plays this role, because that is, of course, a course by itself. But there are various principles in quantum mechanics like uncertainty principle, no cloning theorem, quantum entanglement, etc., which can be used to come up with beautiful protocols for this key distribution and secure it by using this rather than the mathematical hardness or a trusted courier using a human being. For instance, that is the other alternative. And so there are different approaches to this. There are prepare and measure approaches. There are entanglement-based approaches. These are details. They have their pros and cons. But then this is a field which has been very active for several decades, as you can see. We are not very imaginative in the naming. So the name actually contains the date on which the protocol was, proposed. So that is 1984 onwards, we are active in QKD as a community. So now this brings forth the need for the satellite in quantum domain. So far we have been discussing a revolutionary change in how we are securing data transfer by using the key distribution is by using quantum mechanics. But why do we need a satellite for all this? This is because we need long distance quantum communications. So now, and it's a perfect example. I'm in my office at RRI and you guys are sitting in Delhi. And so if I want to communicate with you just by looking at my screen, it's not going to happen. We don't have line of sight. So how am I going to distribute a key between me and the panelists is a question. And of course, while that is not the most interesting question, if our Prime Minister wants to, communicate something with his counterpart in Canada, how is he going to do that in a secure way? There is a distance issue, and that is what is very practically important. Otherwise, what I do in the lab is interesting, but is not practically relevant all the time. So the distance is an important problem, and now we have different approaches in the conventional route. We have the ground-based approach where, of course, we have line of sight based communication. So if I keep seeing you, then I can communicate by using this line of sight. But the earth, unfortunately or fortunately, is round or oblate. So beyond a point, I won't see you, right? And so if I don't see you, then I can't do this. So few hundred kilometers, okay. But beyond that, I can't keep seeing you and doing free space. Then, of course, we have fiber. You would say, why not use fibers? We can use fibers, but then fibers don't, they're not perfect. So beyond a certain distance, fibers have attenuation in the signal. And so beyond a certain point, I cannot keep on sending the signal. I need to sort of repeat and ramp up the signal. I need an amplifier. And that is not possible in the quantum domain because you cannot copy an unknown quantum state. That is no cloning theorem. So the conventional approaches which we use for sending communication beyond a few hundred kilometers, they break down. So we need out-of-the-box solutions. And these are the three solutions which are being, researched globally. One of them is a trusted repeater network, which we won't get into. Then there is the quantum memory-based quantum repeater, which uses entanglement, which again we are not getting into today. The one we want to discuss today is satellite because it's the Indian Space Congress. So how can we use satellite to actually help circumvent this distance problem? And so this is what happens. A satellite actually is in its orbit. It is moving around, whatever satellite that may be. If it is something, let's say in low Earth orbit, which is what we're focusing on right now. So in low Earth orbit, it is moving in its orbit. So it basically bridges a large gap between areas which don't see each other. So even if, India and Canada don't have line of sight, which obviously it doesn't, the satellite will spend, in its orbit sometime over an Indian ground station, sometime over a Canadian ground station. And then, of course, by doing a lot of different operations, we are able to connect these two ground stations using a quantum link. And so satellite bridges this large gap. And that is how we need satellites to increase the distance of quantum security between different countries, between different parts of the same country, which we cannot do by using free space and fiber alone. And so this is what we want to go towards, hopefully in our lifetime. And so this is, the satellite link. As you can see, the satellite has linked, let's say, two ground stations which are thousands of kilometers apart. But then after that, this ground station can link to different service providers. And here we have all these, agencies which will benefit from quantum security, whether it is our data in the hospitals, whether it is the bank, whether it's the defense, whether it is us using our cell phone, for instance. So all these sectors will be benefited, and that can be done by using fiber. So what we are looking at is a hybrid quantum network where we have the satellite bridging the long distance and then the fiber network connecting up the various nodes from these ground stations. So this is the overall picture, and different countries are, very active towards satellite-based quantum communications and not just key distribution, but also other means of quantum communication like teleportation, for instance, and so on and so forth. So this is what the different countries are doing. And so having said that, so this is the general picture as to why we need satellite in quantum. And of course, quantum will also benefit satellites. So maybe we'll have that discussion during the panel where, we can see how different quantum technologies can be flown in space, and that can also benefit different sectors, for instance, quantum sensing. But for now, we want to restrict ourselves to the quantum security aspect. And the next 10 minutes of my talk, I will spend in telling you why I'm giving this talk. And so this is how we began our lab in December 2012. And this is, by the way, Gilles Brassard, who is the BB84's B. One of the Bs in the BB84. So it's very nice that he actually also was participating in the inauguration of our lab, and several other people who many of you must already be familiar with. So now what do we do with photons? So of course we need photons for quantum key distribution. Photon is a particle of light. And a particle of light, using its degrees of freedom, we are able to do this key distribution. So other than quantum communications, which is the focus today, we are also working on quantum information processing, fundamentals, quantum computing, as well as quantum sensing in our lab at RRI. And so these are the various things we're doing in communications, key distribution. As I mentioned, this is what we are focusing on today, but then there are other things to do teleportation, relay and repeater technologies, random number generation, chip-based QKD, which is probably not the the focus of Indian Space Congress, but this is also very important going forward, that we can spread it across different sectors. In quantum computing, we have our own photonic platform, and we are also working with CERN on developing use cases for cloud-based quantum computing. And in sensing, we are doing imaging with entangled photons, as well as generalized measurements towards sensing, and then several ideas in principles of foundations of quantum mechanics, as well as more recently quantum gravity. Okay, so now if you want to know more about photons, because we are at Indian Space Congress, we should not know a lot about photons is the hope. And so then if you want to know more, this is a popular article which I was invited to write, and this is a textbook chapter. So as an academic, even though I am not in person, have to give you some homework. And so this is a textbook chapter that you can read to know a lot about photons and their use in quantum science and technologies. Okay, and so these are the people who make the science and technology happen. Having said that, we have done a lot of work, which I will skip for now. In quantum communication, we are working on India's first project on satellite-based QKD, which is the focus of today's discussion, integrated photonics, teleportation, DI, RNG. So this is, I want to tell you a little bit about what all has already been done. And so, of course, this is very good, important, because people should know that there's already a lot of work that has happened, for instance, in our lab, as well as in others across the country. So our project is called Quantum Experiments with Satellite Technology, or QUEST. And so it's a quest towards satellite-based quantum communications. And so the idea is to establish satellite-based quantum communication between two Indian ground stations using an Indian satellite as a trusted node. Okay, and this is a collaboration with the Indian Space Research Organization, which is ISRO. So why is this experiment exceptional? Well, it is India's first project. And so we started at a time when nobody believed in satellite-based communications. And now we are talking about having this as an important session in Indian Space Congress. So then naturally we have come a long way. And at that time, people were skeptical that this would even happen. And then one of our neighboring countries actually flew a satellite towards quantum security, and that made the science fiction science very quickly for the, the important decision makers of our country. And our project got funded as the first project in this domain. Okay. And so security is important, we have seen. What have the neighboring countries done? This is papers that you can read. And so what they have done is what is called downlink-based QKD. So essentially you fly an entangled photon source or any other photon source, and then you send the photons to the ground station. And then by doing that, you can have a link between two ground stations or more. And so if you have an entangled pair of photons, so one goes to ground station 1, the second goes to ground station 2. So now this is downlink. So one of the problems with this is that, first of all, the entangled photon source has flown away. And so you can't really do much with it after it flies away. I mean, you can't retrieve it and align it a little bit and send it back. That doesn't happen. Secondly, you need simultaneous line of sight between these two ground stations, because they need to go to the two from that satellite. And so it limits the distance over which you can do this. So what we are attempting is what is called uplink-based QKD, where we will have the entangled photons on Earth, and we will send them up to the satellite, from each of the ground stations. And so then we can have the photon source with us, which is very important because it gives us more flexibility with changing the source even after the satellite has been launched. Okay, and then we can include memory elements after the satellite launch. So we can actually do many things which haven't been done before, but of course that is why it is also harder, given that it hasn't been done before. We don't have a lot of literature to actually bank on for various techniques and technologies we need to develop towards uplink-based QKD. And that is why we have been doing this systematically over the last more than 5 years, building up one thing at a time. Okay, and so these are the various things which we have achieved. An in-lab protocol for prepare and measure QKD, which has a competitive key rate and QBA. These are numbers which you use to talk about the rate of the key and the error. And so this was better than the previous recorded, reported such data from a group in NASA. So this was one of our first results from RRI as well as India. Then we went on to demonstrate QKD between two buildings. Okay, so if I want to do satellite-based QKD, I obviously cannot remain within my lab because then there's not much complexity in the problem. So I want to demonstrate this between buildings so that obviously the atmosphere comes in and I can solve those challenges. So this was the first such demonstration in India in February 2021 using entanglement as a resource. More recently, early this year, we went on to demonstrate QKD between a stationary source and a moving receiver platform. Why is this important? because a satellite does not remain stationary on top. It is going to move. So as soon as it moves, I will lose the link, and then I will lose any quantum communication I'm trying to do with it. So I need to develop sophisticated pointing acquisition tracking systems and keep on maintaining this link and looking at it and doing QKD. And so this is what we have achieved by using this moving receiver platform, which gives us all the know-how needed to fly this guy in a satellite. We have done a lot of work towards mitigating different kinds of errors which creep in, because this was the problem earlier, right? A photon is going to go up. Is it really going to happen? Is it not going to get destroyed by the atmosphere? These were the questions which led people to not believe that this sort of thing would work. But then there are obviously actual issues, and so we have solved one of the very important ones in polarization in this most recent work, where we have changed, come up with a new protocol for QKD. And then, we also turned into software developers. So we are doing software development for QKD with device and process imperfections, as well as improving the QKD performance parameters. So these are all various things in a snapshot which we have been able to achieve. So now, this is more to appeal to people like Anindita and Pankaj, who have, come from this particular background of QKD. How did we actually go on to solve some of these problems regarding the kind of attacks which can happen. So now attack, what do I mean by an attack? Now it's not to do with any biological organ. It is essentially this, that we have quantum communication between Alice and Bob, but there is this guy Eve who's trying to get the information. So this trying to get the information is what is called an attack on my QKD, and so we have to come up with different ways to prevent these attacks. And so for our Alice module, we prevented the different kinds of attacks by using novel ideas, which again I'll skip for the current audience, but these were the ways in which we were able to get those results better than the previous ones from the NASA group. Okay, and so these are the snapshots of how things look, a virtual lab visit. Then we have the software development. Now this is very important, because if you really want to develop QKD in the lab, you don't want to, first of all, you may not be rich enough to actually buy all the components, set it up, and then realize something is wrong. Who gives us money to do that, right? So it would be good if you had a simulator which could, simulate things with the imperfections of the device and the process, so that what results you get have a hope of matching with what you will achieve when you can buy those components and set it up. It's also good for the funding agencies to know that you've run it through such a simulator, rather than just ask for several lakhs or crore or whatever it is that you're asking. So this is what was missing in literature in all these simulators which existed, and so this is what we did. We filled these missing requirements, so we can simulate physical processes and ensure that they are not ideal. It's a very interesting negative statement, right? That ensuring something is not ideal, but we cannot help it. That is how experiments are. Devices and processes are not ideal. Better take that non-idealness into account, so that your simulator is more practical and we call it an experimental friendly toolkit. Okay, so this is our little logo. I don't know why we created a logo, but people seem to create logos, so we also created a logo. So we are not thinking of commercializing it right now. We just don't have enough time and wherewithals, but then this is what we have been able to achieve, and by following what is called the AGIFOL model of software development for people who come from that background. And this is important. You can see the beautiful match between the experiment and the simulation. So, if we didn't have the simulators, simulator will give us beautiful results and experiment will always disappoint you. But now you will see that, you have a very close match, and we have different iterations coming up as we speak. These are snapshots of algorithms, which I'll skip. But this is my, important slide here as an academic. Again, this was the previous result, and I love to show that ours is higher and lower in the quantities which matter. And so this is what we were able to achieve. And salient features were various attacks which we were able to remove. And of course, we weren't just happy ourselves. We managed to make some other people happy. So we also got some of the popular media happy, the Nature India people happy, the industry happy, and the government happy, which is the rarest of rare happiness that you can achieve as an academic. So we achieved all this happiness, and then we went on to entanglement-based QKD. Okay, and so this is, again, you can read all this.
You might want to skip that, Dr. Sinha. I think given the nature of the audience, yeah.
So, entanglement-based, I will skip it.
No, okay. Going detailed, maybe you could wrap it up.
Yeah. I have 2 more minutes, actually. So I will not take more than 2 minutes. I just want to go to the slide which is of interest to you. I mean, not to you maybe, but then hopefully to someone, which is this one. So now, what is it that we have done to be able to do satellite QKD using polarization? So this is the graph that we have, and this is the graph you would have if we didn't have our method. And so you can see that the errors would be 60% as opposed to the 10, which is information theoretically secure. And so this is something that should be of interest to anyone who may have interest in using QKD in satellites. Okay?
Right.
So this, of course, I'm not going to talk about this, but this is important that, how do you actually go from within the lab to outside the lab? And, you're sitting inside a nice air-conditioned room, but then this is not where we do QKD if you want to do satellite. So this is how we set things up. This is our ALICE module, which is inside the lab, and then we have now gone out. We have crossed the RRI campus, which is not very big, and we haven't cut any trees, and we have been able to reach our Bob lab, which is, a certain distance across, and then we are able to show very nice results using this approach. Okay, and we were also able to show, that while this is a proof of principle, if you want to increase the distance to few kilometers, you can do that by using standard techniques. You don't need to worry very much about whether your results will drop. So it's 10 to 9 really. So it doesn't matter whether you're 200 meter, 300 meter, or 500 meter. 50 meters does the job for you. Okay. Then this is the moving receiver thing, which is very important. If you really want to do satellite QKD, it's not going to stare at you as a stationary object. And so we have gone through different approaches to how to move the receiver. And I think Anindita wants to do something with the drone. So naturally, you will also have to worry about these aspects as you move along. And so this was our, more recent one, where you can see we have a moving Bob platform. So this is the receiver, which has all the optics and the optomechanics and the time synchronization that is required. And so this guy is obviously a little bit big right now, but we are going to make it smaller and optimize it so that we can then fly it as a payload in our, hopefully, satellite, which ISRO will identify for us in the near future. So this is the moving receiver platform and some appreciation for that. And so I think I have taken less than 20 minutes, Rina. I hope I have satisfied your time requirements.
No, thank you very much. And thank you very much for that outline. And for the benefit of the audience, I also wanted to say that whatever Dr. Urbasi Sinha just talked about shows us, I want to highlight the points that I caught from her presentation, although I've been aware of this for some time, is that we're talking about world-class stuff happening in quantum communications in India, out of a research lab in India. Second thing, what we're talking about is that the space sector may be unaware, not the researchers, but definitely the larger space sector may be unaware of the impact that quantum is going to have on space. But it's important to understand that it's not just theory that we're talking about, and therefore I really appreciate her presentation where she's shown you the actual results and the equipment, etc., that is involved in it. The future of communication is quantum. If you look at ITU and the planning that is happening for 6G and beyond, it is taking into account quantum communications as an integral part of it. From a space communication perspective as well, it is extremely important. In fact, it's not just from the applicability of QKD, but even from the perspective of keeping your satellites secure, or the communication between them secure, or the synchronization that is done for satellites. There are just too many applications that need to be looked at. And one of the reasons I think we are doing this SOL session, as Dr. pointed out, which is focused on quantum in this otherwise space congress, is to start the dialogue is already started because RRI is partnering with ISRO, but then in the larger community to actually have bigger conversations. And on that note, after thanking Dr. Sinha, I want to request all the panelists to actually take 3 minutes to talk a little bit about what is the context of your organization and yourself in this whole conversation around space and quantum. So I would like to start with Pankaj Gupta, and if you could tell us a little bit about what you are focusing on, that will be great.
Thank you, Reena. So basically, I belong to Space Application Center, and the center role is basically to build payloads. So payload is basically the system which basically performs the actual user application task, like in case of DTH payload, the transmission is being done by the payload, and the satellite, I just trying to distinguish, most probably everybody will be knowing that. So now the payload, so now when it is coming to the quantum payload, this is a new domain where these payloads need to be built. So now first of all, what need to be identified is what are the key technologies which are needed to build this payload. So the key technology as far as quantum communication is concerned, which is mature, or which you can say the quantum technology which is reaching to the maturity where application can be conceived, and it can be a very good use case. So here the major technologies which are needed is like quantum source, quantum receivers where detectors are also coming, and third one is the pointing and acquisition and tracking system, so that because when you are like in the LEO, because with the GEO it is bit difficult because losses are very high. So having the communication with the GEO satellite seems bit difficult, but feasibility studies about that also has been done, and GEO will be a very good use case for the regional service operator, because when you look from the business angle, it is very important, because when you are operating in the LEO, you need to have the constellation to offer a service. Whereas in case of GEO, it will be very good for the regional service operators. So this is what, but still in that case, the potential difficulty is the large size telescope on board is needed if you are going for the downlink configuration. And majorly, like Urvashi Sinha said, there are two kind of a configuration, uplink configuration and downlink configuration. So that uplink configuration is being like not being studied still, because in that case what happens, if whatever the perturbation happens in the beginning itself, when you are transmitting uplink, so your atmosphere, whatever the beam deflection happens, then up in the environment only it will happen. After that, in the vacuum, it is not going to happen. So you have to have some compensation mechanism such that whatever the light signal you are sending, which reaches to your satellite, because in optical communication, it is going to be very slow. So now coming to the fourth system, that is timing and synchronization. Fifth one is your post-processing system, or you can say you need the protocols, whatever you wanted to run, whether it is a BB84, BBM92, that or any other protocol, new protocols persons are also seeing. So there you have to have entire post-processing system. And then another one is the polarization acquisition. So these are the 6 major elements which need to be, those technologies need to be built. So because we need to realize the payload, then all these technologies we need to build. So at ISRO also, we carried out 2 building-to-building Fourier space demonstrations. And in that first demonstration, we have demonstrated the 300-meter quantum QKD link with end-to-end application where everything was running automatic system. So as we as a payload, having payload making responsibilities, the end-to-end application demonstration is needed. Similarly, we have also demonstrated in 2021 that entanglement-based 300-meter QKD also. So now with this demonstration, we could realize, or we could test our first version of quantum transmitter, quantum receiver, your timing synchronization system, your post-processing system. The only remaining system is pointing and this polarization compensation technique or polarization tracking module, as well as pointing and acquisition tracking system. So those 2 systems, one is almost ready and we have tested in the lab. And pointing acquisition PAD system, which is also a very crucial system for satellite communication, that we are in the process of making a 300 telescope for the onboard use with a PAD system. So once that is realized, so we most probably will be ready for the payload part, and all these systems we wanted to have, wanted to test first in the onboard. So few experimental payloads also we are making. So soon, so up to a scaled version of all those technologies we can test on board, and any surprises, any improvement can be done, which can be taken up in the whatever the full-fledged payload for the kind of a service-oriented payload we will be making. In that we can rectify those issues and make a better payload. Thank you very much. I think this, I gave a brief summary about the payload making. Now I will hand over.
Thank you very much. Now I request Rohini to talk about the perspective that you have from a space and quantum, where do you, what is Microsoft doing and what are you focused on?
Thank you very much. Can you hear me? First of all, Professor Sinha, you made me want to become a grad student again. It was wonderful, really, really great overview, and very proud to see the kind of work that your lab is doing along with ISRO. I think you really need to accelerate the work in India in this space. Let me give a little perspective from a cloud, hyperscale cloud provider like Microsoft on the kind of areas we are working on, both on the space side as well as on the quantum side. I think the overlaps coming from a computing tech company are going to be interesting, but let me give a little bit of overview. First of all, you might wonder what Microsoft is doing in space. Actually, quite a bit. Because as a hyperscale cloud provider, the number of regions and data centers that we have around the world that are connected by optical fiber makes us a natural partner to the satellite companies in terms of providing that connectivity around the world. Given the kind of really high or low latency and high throughput kind of interconnections we have, especially in this world of AI. Second, what is happening is as the companies are using satellites and bringing data, they want to understand how to leverage that data. So one of the things we are doing is we have something called Azure Orbital, which is a base station that is kept very close to one of our data centers. So if an organization wants to ensure that the satellite data that they need is brought as close as quickly as possible to their use cases, then that is the kind of service that people are deploying for. Especially in today's geopolitical environment, there are a lot of countries, a lot of organizations that are looking at ability to have communication networks in the face of unforeseen circumstances. So there are many things that are happening in the world of communications and space that you would not normally think of Microsoft as being playing in, but actually we are quite active in those spaces. The third area I would speak about is, at the end of the day, especially the private sector, if you're looking to engage in satellites for any of your use cases, you are looking at data. So a lot of the work that is happening on using machine learning, using artificial intelligence for that data is the place where, and be able to then develop any insights from the data. Think about logistics planning, or think about transportation, any of these use cases, or land mass, or disaster recovery. All of these use cases require you to be able to work with those terabytes and petabytes of data in a way that you can develop insights from there. And if you've been following the world of AI, and if you've heard the word ChatGPT, which I'm assuming everybody in this room has heard of, then those technologies today are able to allow you to engage with your data in a conversational style. That is completely changing the nature of the way in which people even engage with data. So those are a few things we are doing in space as a very, very overall overview. If we come to quantum, clearly as a computing company, today the hunger for compute cycles could not be higher. If there is one bottleneck in the world all large tech companies are facing is in compute cycles. And it's AI that's driving that. Whether it is GPUs or TPUs or NPUs, whatever you call it. So people are looking at this next paradigm of computing, which will be quantum computing, as a way in which some of the most intractable problems will get solved, and Microsoft is also among those companies around the world who's investing in that space. The approach that we have taken is that a quantum computer, whenever it is ready at a scale which is what you may call a practical size problem scale, it is not going to work on its own. It's going to become part of a larger computing infrastructure. And you will need to have everything that the software industry has developed over decades and decades in terms of compilers and programming languages and everything that you require to solve a real problem. You will need that what is called a full stack approach. So in our world today, when we are thinking about preparing for the quantum computer of the future, that is going to be of the number of qubits that can solve real world large scale problems. We are making sure that today itself, the ability to plug into quantum hardware from third parties, and there are many out there who are preparing quantum computers based on either superconducting qubits or trapped ion qubits. There are many technologies out there. Microsoft is also following another approach towards developing a stable, high fidelity qubit. But besides that, the ability to solve problems. And I'll give you one example of a space problem that is using quantum computer. So in this case, the Jet Propulsion Laboratory at Caltech, they are working with NASA. And in the earlier some of the sessions, you would have heard that the deep space satellites, their ability to communicate with JPL is a complex scheduling problem. And requires multiple parameters and highly constrained optimization problem. That is one of the problems that they are using quantum techniques for, as an example, of which is really a space scheduling problem, but uses quantum techniques. So I'll pause with that, and we can discuss more later.
Thank you, Rohini. And I will now request Dr. Anindita Banerjee to, talk about CDAC and, what else is happening at the interface of space and quantum.
Thank you, Rohini, and I thank the organizers for giving me this opportunity. So CDAC is working on quantum computing and quantum communication. Quantum computing, because it is based on the principles of quantum information science. It has certain resources like entanglement, superposition, which gives you an advantage of time and precision for computing. And also, computing with lower power, okay, which is because as the problem scales, you have more power consumption, which is actually a problem. In Pune, you have water scarcity. How will you bring your HPCs, run so many HPCs? Cooling is a very important problem. And you have large-scale deployment of HPCs now for many application areas. So now what CDAC is doing in quantum computing, 4 things. One is we have developed a quantum simulator. The simulator is actually a project from IISc Bangalore, from Classroom Project, and we have taken that Classroom Project and put it in the cloud, and that is accessible pan-India. It is called QSIM, okay, and then we are working on use cases around it. Second is we are working on accelerating the simulators on advanced compute hardware like FPGA, GPUs, and vector cards. We are exploring vector cards to how to give some time of a time complexity advancement. Why it is important? Because as I said, we are using quantum computing to solve some large-scale problems or some problems which is difficult for a classical computer to solve in a polynomial time. Madam had presented one problem called, the quantum algorithm is Shor's algorithm, and the security of all the digital communication, the mathematical hardness can actually be broken by Shor's algorithm. So there is some class of problems which falls under some, say, bounded error quantum polynomial class, And you have to find the applications, because I think all the industries have some or the other complexity problems, right? So you have to understand whether that complexity problem falls in that particular domain, then the quantum computer will give you an advantage, okay? So it is important, it is going to work with the classical computer in a hybrid fashion. Then the third area CDAC is working on is establishing a hybrid HPC classical compute infrastructure and trying to implement certain algorithms on a hybrid HPC QC infrastructure. As Madam had, Rohini Madam had clearly said that, the world now is basically quantum assisted algorithms, which will be using HPC to solve certain problem. It will be using HPC for maybe using some machine learning techniques to optimize the error correction, the protocols which happens for a quantum computer. So it is used to it will be using HPCs for different reasons, not particularly one. So CDAC definitely is going to play a role there. Then, of course, skilling, quantum education. We are trying to reach out to different, to remote areas using our cloud and trying to educate the people in quantum, maybe in different languages, regional languages as well. Now that has come to quantum communication. Why quantum communication? Madam had clearly said, Professor Urvashi had clearly said that it is going to solve the security aspects. So quantum can be used as a sword and a shield. You use it as a sword with quantum computing because you can actually cryptanalysis, let me not go into that domain, but it's a very powerful weapon or a tool for different applications. And as a shield, so quantum communication is needed for a shield. Now it is going to play a very important role for integrated 6G, kind of an ecosystem. And we need all kinds of communication, terrestrial, non-terrestrial, and satellite, because each of these has its own limitations, has its own boundaries. So we have to utilize all these three platforms. And CDAC is working, CDAC with IIT Madras, CDAC Bangalore has developed a quantum network, starting with 2 nodes between IIT Madras and SETS. And we are now engaging with other partners to make it a more terminal-oriented kind of a network. And I'm working on non-terrestrial network. See, in space communication, I actually see 3 categories. One is fixed ground-to-ground free space communication. But what I envisage is, if there is a difficult terrain, and if, for example, there is some strategic requirement, and you need to send out the secret keys where satellite is not there, fiber is not there, then that can be achieved using a network of quantum drones, which will actually fly there, deliver the keys, and come back. They cannot stay in the air for a long time. So this kind of application is what we are looking for, and we are starting off with a downlink. We have a transmitter on the drone, and the receivers will be on the ground. And we are also seeing how to use advanced compute hardwares to also address the post-processing challenges and others associated with this area. So I'm actually working in the area where Sir on my right-hand side is working on. And previously, I was working with QNU Labs. There I was heading a fiber-based QKD system. So I was working on how to take a quantum information experiment from a textbook and putting it on table. So right till TRL 4 or 5. And then I was working with product team to how to take it from TRL 4 to 5 to 7 to 8. And the product has also been tested by strategic agencies, and it is up in the market. And so I was working with the gentleman on my left. So this is all I have to say. Thank you.
Thank you. So quantum is a very close-knit community, as you can make out. Everybody knows everybody. I actually joke about it when people ask me how big is the community. I tell them, if I go on LinkedIn, and every single person on the planet working on quantum is either a first-degree connection or a second-degree connection at the most. So, but that connection needs to extend to the space community because there are so many joint applications, and we need to have that conversation. So over to you.
My name is Captain Sood.
Exactly. So I wanted to make sure I don't call you out by the wrong name. So Captain Sood, tell us a little bit about CUNU Labs and what is the current state of the art that's happening there, and especially with respect to what are the plans for space and quantum?
Sure. So, thanks to the organizers for permitting us to be here today. And as already mentioned, there's a sword aspect and there's a shield aspect. And here's the lady sitting on my right, who's seen both the worlds. Yeah. So, CUNU Labs is a startup which is just about 7 years old. And we are proud to say that most of the things that we've been discussing, we already have products which are productionized, some deployed, some ready for deployment. So when it comes to QKDs, we have QKDs available that have been tried out in the Northern Command of the Army. We have established perhaps the longest distance anywhere on this globe using existing fiber. From the QKDs, we also have trusted nodes that allow you to extend. These have also been tested. We also now have the hub and spoke. So whatever sort of implementation that you want to do using QKD today, it's realizable. And as Professor Sinha said, yes, distance is a limitation. And in addition to limitation, it's also how do you protect your QKD nodes and your trusted nodes? They can't be left out in the open. They are temperature sensitive and need physical protection. So yes, that is where the satellite QKD comes in. And once the satellite QKD is added to the other components that you have, you are free to implement whatever network that you desire. So when it comes to satellite QKDs, what we have done so far is we have demonstrated 500 meters of QKD day and night, continuous operation over multiple days. And today we are ready to do a joint demo with ISRO for a 2-kilometer free space QKD. We are awaiting for final location to be identified. And work is ongoing, how to extend beyond the 2 kilometers. In addition, CUNY Labs also offers software-based solutions using PQC, etc., which are available. But broadly, as a small startup with about 70-odd people, this is the array of products and solutions that we have available right now.
Thank you, Captain Sood. And let me take some time to talk about Quantum Ecosystems and Technology Council of India, which is the company that I'm the founder for and I represent. This is a not-for-profit Section 8 company which is focused on enabling and accelerating the quantum ecosystem in India. So we are more like an industry forum, and anybody who succeeds in quantum in India is our success. As long, that's the goal and aim. And so in some senses, we advocate for quantum. And the reason why you need to do that is because it's a little obscure technology. It's not something which is easily understood. It is not mainstream. We can see that, and I'm going to pose a question to you on that, but you can see that by the fact that when the space sector was opened up, you would see it was considered a very difficult sector, and yet you see such a large number of successful startups now in the Indian ecosystem, and you have the investor community which is completely lined up to that. And then they sort of may not understand the technology, but they can see what is happening, and they're sort of investing in that. But quantum is so obscure that you have that challenge a little bit more, right? And I'm sure CUNU Labs has had its fair share of challenges initially in terms of trying to get funding and so on. So that's the reason we have established QETCI. So if anybody who really wants to have a more detailed conversation around space and quantum, please do reach out to us. We are connected to everybody, and we can connect you to the right people and help take the conversation forward as well. That's my 3 minutes, and then I'm going to go ahead and ask the panelists about, when we look at... yeah.
Reena, can I add one comment here that, the interpretation of 3 minutes is also different for each of us.
Sorry,
Isn't
go
that
ahead.
amazing? So the interpretation of 3 minutes is also something which is different for each of the panelists.
Right,
So yours
yeah.
was 2, actually.
Mine was 2,
was-
and you were
yours was-
actually. Okay, thank you.
Yes.
Thank you for being the timekeeper, and I'm glad I saved time for everybody else. But as the moderator, that's my job, right? To give more opportunity to speak to others. So coming back to the group, one of the things that I wanted to talk about is, till now we've heard a lot about the technology and what's going into the system and all of that. And I just introduced the topic about the startups in that space. So my question to the panelists is, where do you think is the sweet spot for the first few startups? You know, some of them are already there, but then where is the sweet spot for more startups to come in? And, you know, please feel free. Each one of you can add.
So like right now, so there are two segments. Yeah. So there are two segments. One is the individual, whatever the technology element I talked about. That is one spot where you can come in and start developing those technologies or generate the product for which can be further integrated upstream, and satellite-based QKD or even the terrestrial QKD can happen. Another sweet spot is something like right now because quantum is something which is right now with a very, you can say, premium institutes. Now, how to take those to the lower level institute with a reduced cost, or something like quantum kits kind of a thing, which right now are being sold by foreign companies at much higher cost. So now you have to think, okay, because multiple fellows are working, so the technology is available. Like at ISRO also, once we have demonstrated the systems like RRI or ISRO, so we have the entire know-how for a static system at least. So now if you wanted to make a product around it and suitably address that market and its use, so depending on how much cost you are able to bring in, so these are the two sweet spot I can just say, okay, this is, or if you are having a bigger investment plan and all that, definitely satellite-based QKD-based services is one of the major thing which you can start. The way QNew is starting.
I also want to add something. See, when we are trying to work on a quantum technology device, it has so many technological challenges. And definitely one organization does not have the capability to address all the challenges. So we have to work together. Now, startup, it has its own challenges. It's very difficult to survive, particularly a hardware-based startup. Now, since I have been in few forums between international and national, so I see that there is a lot of proactiveness from the government side in industry representation. Now, how the industry representation, does it represent the entire industry issues of our country or not, is a separate issue. But they have given a platform so that maybe a startup which they will have limited market, because India doesn't have a quantum market as of now. So they have limited reach out. So government is trying to pull them up and putting them in front of maybe US, maybe Europe, Quad nations. So there are so many interactions government is trying to enable. So we have to help each other and give them proper platforms. And another thing I would like to give an example of a startup which is working in space industry. It is called Artificial Brain. And they are working on solving combinatorial optimization problems for space. For example, finding out the optimal route to collect the debris. And they have won some, in some of the European forums, they have won some award. Then they're also looking at, how to put the Earth or any satellite on the Earth's orbit. So these are very complex problems, and the complexity is increasing exponentially depending upon the different variables. So those are the problems which startups can also pick. They don't need a hardware. And also there are some hardware companies like D-Wave, Amazon Bracket, they're providing them access for till certain number of qubits so that they can experiment on. Then there is another problem like the tail assignment, to identify a plane to a flight so that it will have minimum interconnection time, okay, with some constraints. So the startups can identify such problems and work on it, and they will be funded by the organization. So I wanted to address both the hardware dependent and non-hardware dependent kind of.
Yeah, I think Anandita has already captured the scenario very well. It's an ocean of opportunities to begin with. But anything or anytime you touch hardware in this domain, it's prohibitively expensive. So what is basically required is the end customer, as the awareness grows, perhaps has to come forward and start picking up some costs. Otherwise, left to themselves, a startup without very adequate funding is going to struggle and therefore would be forced to stay into domain of more areas like simulation, into trying to pick up problems like Anandita mentioned, rather than go into pure hardware related developments. That will remain a challenge for some time to come at least.
I think, look, every technology goes through its life cycle. If you look at the space sector, India has done amazing milestones in the space sector. And recently with the space policy and opening up the space sector, there is a lot more openness for the private sector to participate, right? As Microsoft, we signed an MOU with ISRO in December to work on startups that are working in the space sector. We've already been working with the likes of Pixel, and of course, more has to be done. I think in the issue that clearly any startup has to go through, right, is the timeline to be able to sustain the funding and be able to have the market opportunity. As the space sector grows in India, and as the world is looking at India as being a destination in the space sector, especially for satellite launches, I think there are going to be more and more opportunities. Now, if I take those learnings to quantum, again, quantum is, we should not look at quantum as one monolith. Within quantum also there are multiple levels and different rates at which things will move. I do think there are some areas in quantum sensing, in quantum communications there where India could have a very different play, but it is a long game. And I do think that the recent quantum mission from the government is a very important step to invest in a technology that has that life cycle. It does need that kind of impetus from the government to kind of start the ecosystem, and that's what we need to continue on that path.
Yeah, and very rightly, like RRI and ISRO collaboration as being part of that mission also is an interesting, very strong point there. I wanted to delve a little bit deeper.
Reena, hi.
Yeah, hi.
Can I also add a comment on
yes,
this question?
So let me just finish my train of thought and
Yeah.
I'll come back to you.
Yeah, I want to add something on the startups.
On the same thing.
Yeah.
So on the startups itself, I think taking a cue from, you mentioned sensors. And one of the things that I believe is that the sensors is another sweet spot between space and quantum. In the previous session, I was sitting in the other room and listening to a session on natural disaster, disaster prevention. And when you look at disaster prevention, you're relying on communication through satellites a lot. And then you're also, when you're trying to predict disasters, you're looking at relying on sensors. So quantum sensors are much more, that is a space which to me seems like a sweet spot, not just because India has a lot of IoT focus and sensor technology already, but also because the hardware problem is a little less there in the sense that you're still working in the hardware space, you're working in quantum, and you're addressing space-related concerns, but you don't have as much an issue of cost as a communication firm would have or a quantum computing firm would have, because you can manage with a little less. I'm not saying that the issue is not going to be there, but you can still manage it. So I see that as a big sweet spot for the interface of these two technologies. And also, also metrology, right? I mean, synchronizing satellites. I mean, using quantum clocks, right? And some of the latest clocks that are there. So, and there are no firms, startups in India working on that. So I think that's a great opportunity space. Over to you, Dr. Urvashi, for your thoughts as well.
Yeah, so thanks, Reena. So, I mean, just to take that, the sensor thing, I can add a line or two on that. So, the clocks is something, obviously, is something that people are thinking of miniaturizing atomic clocks so that they can be flown and so on. And so that would actually enable, our better GPS. So we would have better navigation. And so that is the idea. But of course, one has to understand that, these atomic clocks, I mean, they work in cold atom space. And so it is a little bit of a challenge to actually miniaturize. And so there is effort going on there already in India. But it's not, I'm not sure I agree with you that it is actually less expensive than quantum communication, for instance. I think it is not cheap. An atomic clock, I mean, I think that was the largest project in the quantum-enabled science and technology.
The sensor space, not
Yeah,
just
sensor.
the
So then,
it depends
so
on
not
this.
just clock.
So
yeah, clocks are part of the metrology sector that you talked about.
Yeah.
In the sensor space, we do have different kinds of sensors available.
Exactly.
And so one of the projects which has been very recently approved in the US, for instance, is about, having these sensors so that they can sense the time change in the Earth's gravity. And that kind of time change can actually help in the kind of problems you were saying that, disaster mitigation, for instance, or being able to predict changes in the weather and so on. So there are these sort of thoughts already being propagated elsewhere. And so I'm sure we need to also work on those areas. And there are already efforts that I know which would sync up with the space. So in fact, RRI is signing an MOU with SAC. ISRO on certain, on some developments in that as well. But then in the startup thing, one thing I think we always tend to forget, and in fact, again, we have forgotten in our current discussion is that, many of these things which we are doing, whether it is in communication or in sensing, requires optics and optomechanics and electronics. And we don't really have a very good company as of now in India, which is making high precision optics and optomechanics. So if I use a stage, for instance, from a company in India, I won't take the name, its precision is much lower than the one I would get from a company in Europe, which we usually tend to buy. And with all this Make in India and the focus on making things in India, we are really getting more behind because we are not being able to buy things. So the margin is more like 8 to 9 months now as opposed to the earlier 4 to 5 to buy something, to make something happen. So the people who are interested in contributing to the quantum space need not always make a QKD protocol or a quantum sensor. If they can actually make higher precision optics, optomechanics, FPGA, logic, even lasers, for instance, then we would really become more self-sufficient. Otherwise, we are going to keep importing. And now we have to import because we are not at that precision level. So that is another startup domain which people should, the entrepreneurs should think of actually working on, because otherwise we're not going to have this self-sufficient quantum ecosystem. We're going to keep importing the high precision things. And at the moment we have a problem because we are not being able to import as easily as we were earlier, but we don't have the solution from India.
Sure, absolutely. I think there is so much to be done at the interface of quantum and electronics and the interface of quantum and semiconductors as well. I think so. We are now starting to get into the.
I will add here. I think ma'am will agree that maybe since quantum optics and precision electronics is such an important part, I think maybe an industry should get in. Because startups will again, they may start working after they get an order, and getting an order is also difficult. But that they should not compromise on the specs, because in quantum domain it is very, very important. It has to be very neat, very small part. Rest is all classical world, best state of the art classical world. Quantum is small, but that has to be precise. That is the problem.
Sure. No, absolutely. I'm not denying that. I'm just trying to clarify to the audience that we are sort of getting into the interface, or getting into the quantum problem side of it more than the quantum and space interface in this conversation now, right? So, and it's a valid point. We have only 5 minutes left. If you don't mind, I'm going to close this conversation now and open it up to the audience so that I'm pretty sure that there must be some questions there in terms of, yes, please.
from Professor Sinha's discourse on quantum technology. I have a few questions to that. Number one, it seems to be a very complex technology, and from what the ISRO rep also said, that the payloads on this aspect are either being developed or they are not yet developed. Thirdly, what you said about quantum cryptography, we are still not in a stage where we can, it's not implementable as a reliable solution to date. This is what is my understanding from this take with respect to classical cryptography. So one question is, what is the timeline, or if we are looking at a timeline when this technology can be brought into the commercial world, so that we can utilize it for whatever, communication or for cryptography or for any other ways. And secondly, the second question is, if it is such prohibitively expensive, like say technology, why are we looking only at startups to get into this field? Why can't maybe the government agencies or maybe the bigwigs like Madam from Microsoft or the other partners, contribute to and give it the Make in India label such that a workaround can be achieved, rather than like what Madam said, procuring things through GEM. So if you could.
I think there's a slight misunderstanding there, if I may say so. QKD technology is productionized. It's available today. It's made in India, designed, developed, manufactured in India. Yes, it is expensive, but it's all available today. It was available yesterday, in fact. So it's not that there's going to be time. Yes, for the satellite QKD, we are working. We have our PAT design done. We need to get it productionized. Sure, as I said, we are doing trials up to 2 kilometers. But that's the way the progression goes. Why government is not investing? Government is investing. Government has created the opportunities, but it is for the industry to buy into it. If you think your existing systems are safe and you are not willing to see the messages that are flying about hacking every day, then we will be exactly where we are today. So technology is there, working on the ground, deployable, provable.
These are also available.
Yes.
So
So I think apart from that, there is something called post-quantum cryptography. And those algorithms, there are algorithms that have been explored and found to be quantum resistant, at least as of now. So there are many companies worldwide who are working on those, and QNO Labs is also working. There are some Indian startups also that are working in that space. The difficult part is the quantum computing part, the second part that you talked about, which requires more investment. Microsoft, I'll let Rohini talk about what Microsoft is doing. But you are right. I totally agree with you that the big conglomerates in India are the ones who should be investing in that space and partnering along with the government to make sure that India has its own several versions of indigenous quantum computers, right, based on different kinds of technology. So we are with you on that. We have to convince one of those conglomerates to actually start investing.
So there is Department of Telecommunications, CDOT. They have a deployable system, and they're also, they have taken this up, and they have a beautiful lab facility you should see. QKD. I'm talking about QKD and PQC. I can give you the reference. You can visit their lab and see several of the QKDs working, and a live link between Sanchar Bhavan and their building. So that can be nice. Yeah. And there are standards available, and this is basically a startup idea, because startups are supposed to do something which is not there already, and then you have standards, and then the companies pitch in. But unfortunately, again, investing on a quantum deep tech startup is again very challenging.
You had a question? Yeah.
I'm Saxena. I'm a physicist by training, and I used to teach quantum mechanics. And see, there are two questions. One is that if the precision systems are being imported, then what are we doing in research? We are just using it as a user, because rest of the things are handled by the hardware. That's one question. The other question, which is very deep, and I have been asking this all the time, that if we are talking about quantum entanglement, then where is the need to communicate? Because the two systems are linked. So why are you talking about communication when the quantum entanglement is already linked within instantaneous situations? You know, that's what Einstein used to call the spooky communication and so on. So this is the number 2 question. Number 3, a lot of people, it gets very fashionable when somebody is talking about quantum, we also talk about quantum. Now the quantum computers, my research tells me, whatever I've tried to analyze, the quantum computers are working only in 1 or 2 labs in the world. And they are using the Josephson junction as the switch and so on, where everybody is talking about quantum computing and there are missions, everything is happening. The I/O devices, the main computer switching systems is absolutely nowhere close to us. So where are we in that? So there are 3 questions. Thank you.
First and second question. No, why if entanglement is there? Yeah, okay.
So, okay, fine. Yes, sir. So, sir, basically the first part of the question was like, why, when we are not making the precision components or something. Okay, fine. So here.
No, it is 100
kilometers. See.
More than 100 kilometers.
This is the setup we have. Now we gradually
Now, sir, your first part of the question was, if we are not making the precision component or precision system. So now, if you will understand the system, so there are different level of technologies. One is the system level technology, another is the subsystem level technology. Further, it can be divided into components level technologies. So fine. So now, different players are needed. This is what the ecosystem is, correct? So now, if ISRO, if I look at from the ISRO perspective, our major aim is to develop, first aim is to demonstrate the system level technologies, fine? Once, then we seek, okay, whatever the resources, so this will be our priority always. Then it will come, okay, the second level of technology, subsystem level technology, can be done in-house, or what are the things can be procured. The procurement come from the industry, local industry or foreign industry. So, but ultimately to make a good system, we have to take a call so that system level things we can make a good system. That's one part. Similarly, another level of technology which is coming is like PIC sensor, which is device level technologies. There also, so based on the focus, everybody works like that. Now coming to that precision, now the problem right now, the precision stages and all what Madam was talking about. Now there are startup persons are working on it, but still whatever the facilities needed to fabricate those fine precision are not available in India. So that's why I think that is becoming the, I discuss with those vendors because I am very much okay, how I can use the Indian made product in our lab, because it should not be, many times it is a bias, okay, always the foreign things are better, but there are certain places limitation, and limitation are because of the ecosystem. So how that ecosystem can be made, and that is not governed by our sentiment, it also governs by the economics.
No, the other thing is we'll be good in some and we have to get better in some areas. So I think we would just leave it at that. And
Ma'am, when we speak about quantum computing, there is a global race about that we have made a 50 qubit computer, a 1000 qubit computer, and we are planning for a million bit computer by 2030, Google's open statement. Now, all these qubits we cannot simply compare because they are enabled on different types of quantum computers. Some may be annealing, or some may be superconducting, or some may be gate type, anything. So where are we in this? Because as per the National Quantum Mission, we are looking for a 50 to 1000 bit computer by 2030, when the world is looking and in 2030 by a million qubit that time.
Can I answer that question actually?
Yeah, sure.
I love answering this question because this question comes in every panel discussion, whether I'm in person or not. First of all, it has nothing to do with quantum in space. Huh? But then in any event, so see, I mean, whoever is asking this question, so you have to understand that there are certain countries who have been working in quantum technologies for 3 to 4 decades, and they have had billions of dollars of funding, concerted funding over the last several years, and that has enabled them to reach a certain stage where they have certain number of qubits that they are claiming, right? And so we talk about IBM, we talk about Google. These are not companies which have come up sort of yesterday. They have been working on this for decades as well. So you have to build bottom up, right? Just because IBM is claiming that they will come up with a 100 qubits, whatever, 1000 qubit system by the end of this year, doesn't mean that we have had the resources so far to be able to make more than the 4 or 5 that we currently have in different labs in India. So we have to obviously build up. I mean, you cannot make 1000 qubit because it's not about adding one qubit and it becoming from 5 to 1000. The complexity changes. And of course, Anindita is very well aware that, it is not, I mean, otherwise high PCI, when you talk about HPC computing, it's not like you just keep on adding a one teraflop or whatever and you get the best HPC tomorrow and today you are just starting. It doesn't happen like that. Any technology you need to build bottom up. And we are, of course, we have a very good number of people who are very committed, who have a lot of experience in building this, and more community building will happen. So we are aiming for something based on our current status, but we're still aiming quite high. This 52,000 that we are claiming. And then there's another misconception I heard from the previous person. It is not that 2 labs in the world have Josephson junction based qubits. There are many, many more than 2, and the orders of magnitude more than that. And in India also we have at least 2 to 3 labs which have Josephson junction based qubits. And that's not the only end of the story. There are ionic qubits, there are photonic qubits. There are different technologies. So this 50,000, these are all numbers based on which technology you're talking about. So ion traps, they have beautiful qubits. They have very, very good error properties, but scaling is a problem. Whereas Josephson junctions, it's easier to scale, but they're not as error-free. So you have to understand whoever's, I mean, it's great that I'm not looking at you because I'm looking at Rohini instead. I don't know, that's my viewpoint. But then, Microsoft, IBM, these are companies which also exist in India. And of course, it would be nice if you came up with, more concerted funding for this. So whatever little funding we have been proposed in National Quantum Mission is not enough for us to actually reach, the million qubits in an 8-year time frame. So this is basically a beginning, and we are hoping that we are going to have that many, and then we are going to scale up. So what people have done in 30, 40 years cannot be done in 6 years or 7 years simply because others have done it. We have to do it ourselves. Otherwise, we can start importing, and that is something we are not necessarily advocating in the mission. We want to build things indigenously, right? And so this is something one needs to understand. It's not just a quantum computing problem, any problem. I hope that answers this question, Reena. I can't hear you, but yeah. Okay, yes.
So since CDAC is aspiring to lead in this way, whatever it'll be allowed to contribute. So let me tell you that what we are saying is we should have a small scale system in India, whether we procure it from outside or not, because we want to build everything around it. So a processor is an important part, but everything is not about the processor. It is actually how am I going to use the processor. So we have an HPC, we have a software ecosystem, we have industry to touch and feel the subject. So we are talking about the entire ecosystem. Then again, 3 years, 5 years, and 8 years, 50, 100. So once you have attained 50, then it's very fast. So critical is 20. So maybe supporting what the CDAC plans, and also that I think the government is also feeling that they will support 3 to more than 1 types of hardware, quantum hardwares for the next 3 years, and thereafter understand which is going to scale forward, or is there any new development on qubit, and take it forward. So government is also discussing with different stakeholders as how to reach that milestone. 1000 is also very ambitious, as Madam has already mentioned. It's very ambitious. Once you know India has made it till 20, you should be assured that it's going to then come out. Thanks.
All right, thank you so much to all the panelists, and we have actually run out of time, and the anchor is here. So we'll.
Yes, please. Ladies and gentlemen, I guess it's a very informative topic. We would like this discussion to probably continue on the tea area. The hot teas are waiting. And the next session would be there in the Oval where you had the inauguration, no parallel sessions. So you all are welcomed there. Please, I would like to move for the tea sessions, please. Thank you, Chair. Thank you, panelists. Very wonderful session.
Thank you.